That's better. My name's Steve Maull. I'm from Cincinnati, Ohio. I own Maull Biomedical Training. Everybody has a manual in front of you. Yeah, we're going to do it's a 1 hour introduction to contrast injectors, just what they are, different types, basic operation of how they work. My background, I graduated from Miami University. That's the one in Ohio. After I graduated from college, I joined the Air Force. I was in the Air Force for 11 years. And while I was in the Air Force, the first 7 years I was an actual BMET. The last 4 years I was a BMET instructor. And during that time, I realized I like teaching this stuff more than actually doing it. So when I got out, when I got out of the Air Force, I wanted to stay in training. So I ended up going to a company in Ohio. Everybody's heard of RSTI? Okay, so at the time, we're talking 2001, they had a competitor. It was called Ditech. I went to work for that competitor. I was with them for about 7 years. And then in 2008, I left them and started Maull Biomedical to teach contrast injectors. I've been doing that ever since. Now, anybody in here have any previous knowledge or experience with contrast injectors? Just Bob. All right. That's expected. A little bit? Yeah. So, all right. So before I tell you that, I got to tell you this. All right. Imaging folks in here? Anybody have imaging backgrounds? A couple of you? All right. So what these machines are for is to help blood vessels show up on X-ray images. So before we get to that, I'm gonna cover how X-ray images are produced real quick. All right. So just take your typical rad room. All right. Typical what civilians think of as an X-ray room. Table, patient's on the table. There's an X-ray tube above the table that fires X-rays into the patient. And inside or underneath the table is some imaging capturing device that used to be film. Now it's a CR plate or a DR. Well, now I think it's primarily DR plates now, digital radiography. So how this works, all right, let's pretend it's film. It's the easiest way to think of this. There's film underneath the table, right? Patient's lying on the table. So the X-rays that come out of the X-ray tube, we're going to fire the X-rays. All the X-rays that come out of the X-ray tube go into the patient. It's not 100% true, but for our explanation, we'll just go with that. All right. So the radiation goes into the patient. Now, some of the radiation that goes into the patient is going to get absorbed by the patient, and some of the radiation that goes into the patient is going to pass through the patient and strike that piece of film underneath or be on the other side of the patient. Now, that film, the image of that film is going to start off as a white blank slate. All right. Now, what makes that film turn dark in some areas is the radiation. The more radiation that strikes the film, the darker those areas get. So the parts of the film that get struck by radiation turn dark. The parts of the radiation or the parts of the film that don't get struck by radiation stay white, right? And that's how you get your typical, chest X-ray, the ribs and the spine and all that sort of thing. Now, when the radiation goes into the patient, two things happen, two things happen. It's been a while since I did this. Some of the radiation goes into the patient, gets absorbed by the patient. Like I said, some passes through the patient. Now, the odds that the X-ray photon are going to pass through the patient and strike that film on the other side is dependent upon the thickness and the density of the body part that particular X-ray photon comes in contact with. The thicker and the denser the body part, the more likely that X-ray photon is to be absorbed by the patient. The thinner and less dense the body part that X-ray photon deals with is more likely to get through and strike the plate. So bone is, compared to soft tissue around it, bone is thicker and denser than the other soft tissue body parts. So that's why bone shows up very well on X-ray images as a white image, because bone is thick, it's dense, it absorbs the X-rays that strike it. So those X-ray photons don't strike the plate that are underneath, that are shielded by the bony part of the body. The soft tissue is less thick, less dense, so we have to get the radiation level coming out of there just right. So the X-rays, some X-rays get absorbed, but the X-rays that get through are strong enough to get through and strike the plate and turn those parts of the image dark. Okay. Now you have to have, for a good X-ray image, you have to have some of both. Okay. I mean, if you think about it, if all the X-rays that go into the patient are absorbed by the patient, that means none of it hits the plate, white image, right? If all the radiation that we fire in the patient passes right through the patient, strikes the entire plate, it's all black, right? So we have to have some absorption and some penetration. All right, everybody get that? All right, now, blood vessels. Blood vessels don't typically show up on X-ray images because blood vessels compared to bone are neither thick nor dense, all right? Now, that's why blood vessels don't typically show up on an X-ray image. Now, most of the time, we don't care. We're here to see if this bone is broken or cracked or whatever. I don't care about the blood vessels, but sometimes we do care about the blood vessels. Sometimes we do want to see it. So what we have to do is we have to put something in the blood to make the blood absorb the radiation so that the blood vessels now show up on the X-ray image. And that's what that is, all right? That's a pump that during the X-ray procedure, literally as we're firing radiation to the patient, We're going to turn that on, and we're going to fire fluid into the patient's veins and arteries to fill those veins and arteries up while the radiation is striking it. So those veins and arteries absorb the radiation and show up as a nice bright area on the film. Okay, and that's called contrast. All right, the fluid that does that. Is that clear with everybody? Everybody good? Any questions? All right, perfect. Now, you said this was working. All right. So what I just described to you is referred to as angiography. Angio means blood, ography means the viewing of, so angiography is the viewing of blood vessels. It's a procedure performed to view the blood vessels after making them radiopaque. Now this image right here, this is a brain scan right here, and you can see how fine, I mean, the white background is basically the plate or the IR plate that caught it. The black areas, dark areas here, those are the blood vessels filled with contrast. So if there were none of this fluid in this machine, this entire image would be pretty much clear or pretty much white. You can see the thicker or the darker areas and how thick some of them are filled with contrast and how well they show up. As a matter of fact, you can see how hair thin some of the blood vessels are that have just literally microliters of contrast fluid in them, but that's still strong enough to actually create the image that we're looking for. So the fluid is very, very effective at blocking radiation. I'll get to a little bit of the science of how it does it here in just a little bit. Generally, angiographic procedures are one of 3 types. Now, there's a bunch of types of different models, but when it comes to the types of contrast injectors, there's 3, all right? CT, MR, and angio. CT is a CT system, MR is your MRI systems, and then the angio, it's referred to angio, but that's typically your more traditional X-ray system, the X-ray tube, and then the patient, and the film plate underneath it. Each of the systems uses the contrast injector to inject the fluid into the patient to improve, or in some cases, make it at all possible to view the images. The images produced are referred to as angiograms or angiographs. And everything that I'm talking about up here, if you want to follow along in the book, you can. Now, I'm telling you, I used to teach this like almost every week, and now I teach it like once a year because we've automated the training. So I'm not as sharp at this as I used to be. I got to go back and read what I got to talk about here. CT and MR injectors. All right, here we go. All right, so for CT and MR systems, they use an IV needle to put the fluid in the patient. All right, it can go to the back of the hand here, things like that. For angiographic procedures, and I think I'll talk about why here in just a little bit. For angiographic procedures, they don't use an IV needle, they use a catheter, right? And they'll take the catheter and they'll insert it into the femoral artery or the femoral vein, and they can snake it up to different parts of the body. A catheter is just basically a really, really long, thin tube that will go into here, but we want to get the tip of this catheter into like the chamber of the heart or one of the arteries around the heart or something like that. So we can go specifically, we can shoot the contrast specifically into this body part while we're viewing the body part. Whereas CT and MRI, it's just an IV needle, and we're basically just lighting the whole patient up, all right, over a very long, or a longer, slower injection. So that's the biggest difference between the two. The body just gets rid of the contrast fluid over the next 12 to 24 hours through the kidneys. Some people are allergic to contrast. If you're allergic to shellfish, you might have an allergic reaction to contrast. I think they typically ask you that before they do the procedure. So that's just one drawback of it that some people have an issue with. Now, when it comes to contrast injectors, there are, here in the United States, there's three dogs in this fight, and there's an absolute pecking order amongst the 3. The biggest company by far used to be called MedRad. A lot of people still refer to them as MedRad, but it's been about 6 to 7 years since then. They got bought out by a company called Bayer. Bayer makes the aspirin and stuff. They're by far the biggest manufacturer of contrast injectors. Probably 90% of all contrast injectors in the United States are Bayer MedRad injectors. And their most common ones are the Mark 7 and the Provis are their angio injectors, the Stellit CT systems, and the MR Experience and Spectra Solaris is for the MR systems. Way down the line, distant second is, you know what? Since I last told this story, these 2 might have switched now. Actually, now that I'm thinking about it, in the last year or 2, this company, where did I go? This company down here, they've come on strong. So probably the second biggest company now is, like I have third last time I wrote this, Bracco ECM. Basically, what they've done is they've gone to hospitals and said, we will give you the contrast injector. You just have to sign a contract with us to buy all your fluids and your syringes from us, and service contract as well, right? So these injectors here, and they're nice. The ASIS CVI is an angio injector, and then they have the Empower CT and the Empower MR injectors. These just came on strong in the last couple of years. Just all of a sudden, I'm getting requests for training on them every week, where before it's a couple times a year, someone would say, hey, you got ASIS training or something like that. So yeah, these guys have come along strong, but they are like literally like 5-7% of all contrast injectors belong to these guys down here. Bayer Medrad dominates the market. And then the last company down here, these are the names over the last several years: Liebel Florsheim, Mallinckrodt, Covidien, Tyco. Actually, I don't think they're even Tyco anymore. I haven't even updated this. I think in the last year they got bought by somebody else, so they're called something else now. Gurbet, yeah, company called now they're called Gurbet. I got to update this slide. They have OptiVantage, Ingemat Illumina, OptiStar, LE. Not overly popular injectors. As a matter of fact, I only really do training on these two. I never do training on these because nobody ever asked for it. But even these two right here, I do maybe 3 or 4 times a year versus all the other ones every class 15 times a year. Yep. Now, how this contrast works, all right? So we have 3 different kinds of contrast injectors: CT, MR, and angio. Now, MR systems, MRI systems, they don't use radiation to produce the image. They use magnetic field and coils that detect electronic impulses coming from the patient during the procedure, all right? So it basically uses electronic coils and a magnet to produce the images. That's MRI. CT and angio injectors, they do use X-ray tubes. They use X-ray tubes to fire radiation through the patient to create the image. Now, the reason I'm bringing up, the reason that's important, when it comes to the fluids, all right, so this is my syringe that this fluid goes into. I'll go into more detail about this later. So this is what the fluid goes into, these syringes right here. Now, for CT and angio injectors, the systems that use X-ray tubes to produce the image, use radiation. The fluid in here is called contrast fluid. The magic ingredient in this is iodine. I don't know exactly what it is about iodine that makes it block X-rays, but it blocks X-rays like a champ. All right. So the magic ingredient in contrast fluid for CT and angio injectors is iodine. Iodine molecularly or atomically just blocks X-rays. All right. Now, since MRI injectors don't use radiation to produce the image, they don't use X-rays, an iodine-based contrast fluid does absolutely nothing. All right. So for MRI, it's the exact same setup, syringe, and it's a clear fluid and everything, but the magic ingredient in MRI injector contrast fluid is gadolinium. What gadolinium does, without going into detail about how an MRI image is produced, basically, well, here's how it's produced. The most scientific way I can put it, it's magic. You just have to hit the I believe button. Put him in a magnet, you get the image. No, basically what happens is, the reason for the magnetic field is they place the patient in the magnetic field, and your hydrogen atoms, which your body's 7% water, water's H2O, so you have an abundance of hydrogen atoms. It polarizes your hydrogen atoms. Remember your high school science, hydrogen has 1 electron in its orbital shell spinning around the nucleus. When you put a patient in that magnetic field, that nucleus is going to get polarized. Wherever that electron is, when it gets trapped by get caught by the magnetic field, it's going to get caught by the North Pole or the South Pole. So they inject electronically, fire electronic impulses into the patient. And so I'm going to go in more detail than I intended to, but let's say this is the nucleus of that electron, or that hydrogen atom. And that 1 electron is stuck up here at the North Pole. When that RF pulse is being injected into the patient's area, and there'll be like let's say it's like a knee, we're looking for a torn ACL, they'll put this big contraption around the knee. That is what is injecting the pulses into the patient's body and collecting the echoes of those pulses when it comes back. So here's my nucleus, here's my electron. As the RF pulse is being applied to that patient's body part, my electron up here will recess off its axis, like pulling the bow of an arrow, or pulling the bow of a bow and arrow. Okay, so that electron precesses off its axis. So it's taking energy to pull it off. All right, then that RF pulse is going to be taken away. When that pulse is taken away, that electron precesses back to its axis. And as it precesses back, it gives back a little pulse of energy. And that little pulse of energy that that electron gives up when it precesses back to its axis is picked up by that coil around that patient's body part. We're going to do that billions of times over the next 20 to 30 minutes, all right? And over those 20 and 30 minutes, all those little RF pulse echoes that come back to the coil produce an MRI image, okay? Now, how contrast deals with that, all right? So the more that electron gets pulled off its axis, and then the RF pulse is removed, the stronger that electronic pulse, that RF pulse comes back. So if we precess off just a little bit, it's a tiny pulse. Precess off a lot, big pulse, all right? What the gadolinium does is it dampens the effect of the magnetic field on the hydrogen atom. So now this hydrogen atom is surrounded by gadolinium. When that RF pulse is applied, the electron doesn't really recess off the axis, all right? So basically little to no pulse, meaning white image, all right? So that's how contrast, that's how gadolinium makes the same effect as iodine does, but for MR injectors. A bunch of information you will never ever need to know unless you're on Jeopardy or something like this. That will never come up while you're troubleshooting a contrast injector. So intravenous fluid, fluid highlights the blood structure and highlights the blood vessels, enhances the structure of the organ. So this right here, you can see, this is an image of the heart. And then this right here is the aorta. Now the aorta is about the size, about the thickness of your thumb, where your heart is about the size of your fist. So the heart back here is a much thicker, denser body part than the aorta, the main artery that comes off of it. This is a smaller, less dense object, but because it currently has this this is an X-ray image. So because this currently has the contrast fluid in it, the X-rays aren't passing through the skinnier body part, the aorta here, where in the background you can barely make out the heart because it doesn't have contrast in it at this particular moment. So the X-rays are passing through it and basically blacking it out, making the blood vessel show up much brighter. Okay. Now in photography, like the difference between dark and light is called the contrast of the image. If it's too light gray and light gray, that's low contrast. Black and white, that's high contrast. It's called contrast fluid because on the image it just increases the contrast of the body part we're looking at compared to the rest of the image. Once the contrast is injected into the bloodstream, it circulates throughout the body, and that's another thing that the operators do have to keep in mind when they're doing this. They don't have to keep it in mind, but they're aware. They've been trained. But if I'm going to take an image of this blood vessel right here, okay, I can't inject the fluid because the patient's alive. The patient's heart is beating. So as soon as you inject the fluid here, it's literally going to be here for about 1 second. Heart beats, it moves. Heart beats again, it moves. So it's constantly a moving target. So that's something that the operators do have to take into consideration and compensate for when they're doing these X-ray images. That we can't just inject this contrast and then set it up and shoot it. There's timing. There has to be coordinated timing between the imaging system and the contrast injector. The beam passing through the patient in the case of X-ray and CT, or the energy released from the patient in the case of MR, is weakened anatomical structure by the process and show up as lighter areas on the image. Stop me or call it out if you have a question. And I just talked about this. For X-ray and CT, it's iodine. For MRI, it's gadolinium. All right, any questions so far? All right, so getting on the equipment. I'm going to stray from the presentation here a little bit. So this right here, this is the Stellant. This is a CT injector. This is by far the most common CT injector in the world. All right, the MedRad Stellant. There is a newer version of this. It's called the Stellant Flex, but it's pretty much identical. They just kind of updated some of the internal stuff, but externally it's pretty much exactly the same. So right here, so I have my injector head, and there's my syringe on one side, and this then actually has 2 syringes. One syringe, and spoiler alert, the green side is contrast fluid. The blue side is saline or water. So this is the contrast fluid, and this is basically what they refer to as the flush solution. There's a few purposes of this fluid, but primarily this is the fluid that does that. This is the fluid that basically keeps this together or helps push this out of the body or out of the heart chambers once the injection is complete. So you see the forward and reverse buttons here. I'm going to talk about that here in a second. And then we have our display over here. Now, Give me a second. When it comes to shooting a shot, okay, the operator has to enter the protocol that they want to shoot the patient with. Now, having said that, they rarely actually, enter, the actual protocol. Pretty much like in this X-ray room right here, they'll have a handful of procedures they actually do in this room. All right, they don't do every single thing under the sun in this particular room. So they'll have like 4 or 5 or 6 protocols stored in memory that they know that they use this room for. So then when the patient shows up, they don't go in there and they start typing all the numbers. They'll just say, yeah, it's an AD chest or AP chest, anterior posterior chest, meaning goes in the front, out the back, so things like that. So they'll just go to memory and pull it up instead of typing in all the numbers. But I know some of you might not be able to see these numbers, but over here, so you see my 2 syringes right here. All right, blue and green syringes. The green is contrast, blue is saline, and this display shows you the volume in it. Then you see this line right here. I'm gonna go a little bit ahead, but I'll catch you guys up. This first line right here, that's referred to as a phase, and that's the first line of the injection. And this, you'll notice that it's green. So green meaning, green is the color code for contrast, so we're gonna shoot green. This first column right here, that's your flow rate. The second column is the volume. And then the third column is the time of that. So if I want to shoot an injection, I'm going to do this one first. Let's say I'll do a volume of 20 milliliters, and I'm going to shoot that at a rate of 5 milliliters per second. Okay. So the flow rate is the speed of the injection, and the volume is how much we're going to inject. All right. 2 different things. Is everybody here not a BMAT? Okay. So I can assume some things. All right. So that's your flow rate, your volume. And then the third thing that the operator has to select, there's a bunch of things the operator can, there's a lot of parameters that they can enter and store and things like that. But there's 3 that have to be selected. You can't do an injection without these 3 parameters, and that's flow rate, volume, and the third one is something called pressure limit, which I'm gonna go into greater detail here in just a little bit. There's pauses, there's delays, there's rise and fall times they can enter, but those things don't have to be. Those can be zeros, all right? But these 3 things, flow rate, volume, and pressure limit, they have to have some value, all right? Again, the flow rate or the volume is how much fluid we're gonna fire into the patient. The flow rate is the speed at which we'll fire that fluid into the patient. And then the pressure limit is the maximum pressure that we will allow to build up in the syringe during the actual injection. And I'll talk, like I said, I'll go into great detail about that here in just a little bit. Actually, I'm going to talk about it right now. My bad. All right, so I told you it's been a while. My timing is off. So let's say this is my patient. We're all set up, and so when we fill the syringe up, this is referred to as a fill tube, and this goes on here like that, and then you're going to have some container of fluid, contrast or saline, and then you put the bottle up there, and then obviously this has to be drawn. This will go all the way to the top first, and then once it's drawn up, then we'll reverse it, pull the fluid into it, and then now my syringe has fluid in it. And then same thing on the contrast side. Now, once my syringes have fluid in them, now we have to connect the syringe or the injector to the patient, and that's what this tubing is for. It's longer and it's coiled, and it's one connector goes to the contrast side, the other connector goes to the saline side, and then this tube here is what goes to the patient, the IV needle, wherever the IV needle may be. All right. Now, so when we do an injection, what do I got? 5 and 20. All right. So let's say we're going to do an injection into a patient. All right. So I'm going to talk about. Everybody understands what flow rate and volume is, I assume. If you don't, let me know. Pressure limit. This is an important concept, but it's a very misunderstood concept by even the techs sometimes. The pressure limit is how much, and we talk in PSI, how much pressure will we allow to build up in the syringe during the actual injection? And that's the important part, all right? The important part that's misunderstood. The pressure limit is the pressure in the syringe, not the patient, all right? A typical CT injection, our pressure limit, we'll set it to 300 PSI. 300 PSI. All right, your car tire is like 28 or 30 PSI. All right, we're going to allow up to 300 pounds of pressure build up in the syringe. And no, obviously, that is not the pressure we're going to put into the patient's veins. Any infusion pump folks here? Anybody know what's the alarm? What pressure does an infusion pump go? Whoa, stop. Roughly, like 8, 10, 12 psi. All right. If an infusion pump hits 10 psi, it shuts off and alarms go off. All right. This one will go up to 300 psi. MR injectors, same thing. Angio injectors go up to 300 psi. Angio, did I say angio? CT and MR injectors will go to 300 psi. I'll talk about why that is in a minute. Angio injectors, they'll go up to 1,000 or 1,200 psi. 1,000 pounds of pressure in a syringe like that. Right? Of course, this is not going into the patient. What happens is, and it's just due to fluid dynamics, it's like right here in my syringe, all right, is about a 1.5 inch wide bore full of fluid, and we're going to shove it out of this little, literally half a centimeter wide, or not even that, a 3 millimeter wide hole out the top here. All right. So as you're doing that, pressure will build up into the syringe. All right, as we're trying to get this massive amount of fluid through this tiny little tube to the patient. So the pressure that builds up in the syringe can get up to 300 psi before it alarms. Once it gets to the tubing, this thin tubing, we're literally in the low single digits of pressure. Okay, so no, when we get to the patient, it's very low pressure. That the pressure limit we're selecting here is maximum pressure into the syringe so that the syringe doesn't rupture during the actual injection. And if you think about it this way. So let's say I have a 200 milliliter syringe here and it's full of fluid, 200 milliliters worth of fluid, and I want to shoot it at 1 milliliter per second. So that means I'm going to empty the syringe over the next 200 seconds. It's going to take 3 minutes and 20 seconds to empty the syringe, but I'm shooting it at 1 milliliter per second. That's very, very low flow rate. Or that is a low flow rate. That's a very, very low pressure. I mean, we're barely going to even register any pressure inside the syringe. But, and you can't do this, but let's say we could. Let's say 200 milliliters of fluid, and I want to shoot it at a rate of 200 milliliters per second. You can only go up to 10, but let's say I could go 200 milliliters per second. That means I'm going to empty this syringe out of this tiny little hole here in 1 second. That would be a huge amount of pressure in the syringe. So the primary determinant of how much pressure builds up in the syringe is the flow rate. There's a couple other things that affect it a tiny bit, the length of the tubing, the thickness of the tubing, things like that. But the primary determinant of how much pressure builds up in the syringe is the speed of the injection, how fast we're trying to shove all the fluid out of here. All right. And another thing too, when it comes to pressure limit, all right, so the 3 parameters, we have flow rate, volume, and pressure limit. If I have a flow rate of 5, a volume of 20, and a pressure limit of 300, when we do the injection, I want a flow rate of 5 milliliters per second. Not 4 milliliters per second, not 6 milliliters per second. I want 5 milliliters per second. I want to inject 20 milliliters, not 15, not 25, 20. All right. But the 300 psi, that's just the maximum. If we register no pressure during this injection for whatever reason, but we get our flow rate and our volume, but 5 psi, 10 psi, that's fine. We don't care about that. That's not the goal. We're just saying don't go higher than that. Right. Anything below that, and we're good. So keep that in mind. All right. Let's see what I forgot. So yeah, the pressure limit is a safety feature, but it's not. It is for the patient, but not really for the patient. It's more safety feature so the syringe doesn't rupture during the actual injection, which it is remarkably rare. It does happen sometimes. The contrast syringes, and this is true of all syringes, the contrast syringes are one-time use only, at least here in the United States. Some other countries push that, but here in the United States, like every syringe, one-time use only. They use it, procedure's done, it literally gets thrown away. And with just a couple exceptions, we do training on 13 different models of contrast injectors. There's only 2 exceptions to this rule. Every injector model, the syringe is unique to that model. Like this is a Stellant injector. Those Stellant syringes don't fit on anything else but a Stellant. Spectra Solaris syringes don't fit on anything but a Spectra Solaris. And that's like that all the way down the line. There's 2 exceptions to that, but it's pretty rare. All right. So pressure limiting protects the syringe from bursting. And to be honest, I've seen it 100 times. I've been doing this since 2008. I've seen probably 100 syringes rupture during training. it doesn't go off like a grenade. It kind of goes off like a shotgun. Just the end of the syringe just blows off at the end. So it's not like everything in the room gets doused. It just, whatever direction the injector's pointed at, that area just gets fluid spread all over it. So you don't have to worry about, like I said, it doesn't go off like a bomb. Now, here's the point. All right, so let's say, so you can guess, all right? If we're doing an injection and for whatever reason, we actually hit the pressure limit. We set the pressure limit to 300 PSI during this injection. Yep, we hit 300 PSI. What does the injector do about it? Anybody know? What do you think it would do? Spit an alarm? Doesn't back up. Nope. But also, the big thing it doesn't do is it doesn't stop the injection. That's usually what people guess, all right? The injection stops. No, infusion pumps do that. Infusion pumps hit that 10 PSI or 8 PSI or whatever it's set to, it stops, alarms goes off, and the nurses come in and make the necessary adjustments. Contrast injectors don't do that, all right? If it hits the pressure limit, it doesn't stop the injection. Now, the reason for that is, and it's a good reason if you once you think about it, other than contrast and fluid, what else at this exact moment are we firing into the patient? X-rays, all right? If that injector stops, we gotta do this all again, which means all the radiation we fired in the patient was for nothing. All the fluid we fired in the patient was for nothing. So what the injector does is, instead of just stopping, it just slows down, backs off on the flow rate, right? So we're doing a flow rate of 5 milliliters per second and we hit 300 PSI and the system senses that. What it'll do is it'll just slow down a little bit. Maybe a flow rate of 4.8 milliliters per second is enough to get this done. It might be indiscernible on the image, all right? All we know is if the injector stops, we definitely have to do it over again. We might have to do this over again anyway, all right? But if we stop, we definitely have to do it over again. If we let it finish its shot, we might still have a good shot. So that's why the injector doesn't stop the injection, it just slows down. And there's an audible beep, and I mean, everybody in the room knows that it's happened, but typically, pressure limits are very, very rare in the real world because everybody knows you can shoot these shots to produce these pressures. And typically, if you're getting a pressure limit alarm, it's because the system is misreading the pressure. It'll say, yeah, I'm hitting 300 PSI when it's not actually hitting 300 PSI. It's for whatever reason, we're only getting to like 200 PSI, but the machine needs calibration and we need to crank that back up. That's actually 300 PSI, but the machine, it's only 200 PSI, but the machine thinks we're at 300 PSI, so it slows down. So typically when you have pressure limit problems, it's not a real pressure limit problem, meaning we actually overpressured it. It's typically the system needs recalibration for something like that. It's very, very, very rare, but that's the case. Things that affect pressure, like I said, the major thing that affects pressure is the flow rate, the speed of the injection. The other two things that can affect it, has a smaller effect on it, viscosity or the thickness of the fluid. Contrast fluid, while it is all clear, it is very, very thin, but it's not as thin. It's not as thin as water. All right, there is a slight syrupy texture to it, and we shoot this through relatively thin tubing, and it's through a very thin IV needle, tiny little 20 gauge needle, something like, or not 20 gauge, 29, 30 gauge IV needle, something like that. Or if it's a catheter, I mean, an IV needle is only like that long. Catheter can be like that long. It's the same incredibly thin tube the entire length. So it takes a lot of force to get that fluid through there. So the thickness and the length of the tubing can also have a small effect on the pressure that gets built up in the system during the injection. And I forgot, and the thickness of the liquid. Now, one of the things that, I don't think I have one anymore. Nope, it got busted during class. There are warmers that they use for these contrast injectors. Because remember, the syringe or the contrast is there's a slight syrupy texture to it. So what happens, one of the things you can do to decrease the viscosity or make thicker fluid thinner, like syrup, is warm it up. We warm it up, it makes it a little more runny, so it'll flow easier through the incredibly thin tubing. So what they'll do is the contrast here that they filled with the bottle, that contrast bottle will be kept in a warmer. So when it's time to fill the syringe, they'll get the bottle out of the warmer, fill it up, and then if the patient's on the table right away, they'll just use it. But if the patient's not going to be here for a while, they'll take the syringe off, and then they'll put the syringe in a warmer. And then when the patient shows up, they'll get it out, put it back on, and fire away. But what they do is to keep the fluid in the syringe warm while it's not in the warmer, there is a little clamp that goes over it, and it's just a little heater. It won't heat the contrast up, but if it's got coils on it that warms up to 38, 37 degrees Celsius body temperature. So they'll just clamp it around the syringe, and it'll help keep the contrast and saline warm longer than if it was just sitting there without the warm on it. They don't use warmers nearly as much as they used to. One, I wish I had one. It's literally a stupid little plastic sleeve, literally with just one little wire hanging out of it that plugs into the injector head to power it. It looks like you get it out of a Cracker Jack box, a big Cracker Jack box, but it looks like a toy, right? It's $1,300 for that stupid thing, non-repairable. When the little red light on it goes off, that means it doesn't work anymore. You just throw it away and you have to buy a new one. They last several years, but they're freakishly expensive. And for a lot of procedures, I mean, these things have been around since like the 60s, and technology has really increased to the point that now a procedure that even 20 years ago took like 10 minutes, a CT procedure, but took like 10 minutes, now it's 30 seconds. All right, so the system's not sitting out there with the contrast at room temperature as long as it used to. So a lot of places don't have heaters just because their systems are so quick, bang, bang, and it's over like very, very quickly. The fluid just doesn't have time to cool off. And people will ask, well, why is there a heater for the saline fluid? Saline's water. You can't make it, warming it up doesn't lower the viscosity at all. But there are a lot of options where they'll shoot the two fluids together. Contrast and saline will get fired together, a diluted version of it, where they'll shoot a little bit of saline, followed by contrast, followed by saline. Well, if the saline's at 37 degrees Celsius, or is it 98 degrees Fahrenheit body temperature, and the solution or the saline is at 70 degrees room temperature, it'll cool it off, which defeats the purpose of us warming it up. So they'll keep the fluid in both syringes warmed up if they think that might be an issue. All right. Any questions so far? Am I doing on time? Please tell me it's not like 5 after. All right, or 5 till, that'd be even worse. Contrast injectors, all contrast injectors without exception, all right? There's 3 components to every single contrast injector. There's the head right here, there's the display, which I've been doing, and then behind it is the white box, and that's the power supplies. All contrast injectors, CT, MR, angio, make, model, manufacturer, doesn't matter. 3 components: head, display, power supply. There we go. I actually talked about this already. Talked about the syringes. Some hold one syringe filled with contrast, some hold 2. Some contrast, well, general rule of thumb, remember there's 3 kinds of contrast injectors: CT, MR, and angio. CT and MR use 2 syringes, pretty much always. There are some CT injectors that just have a contrast syringe, but they are pretty rare, very rare. Most CT injectors will be a dual head syringe, dual head injector, meaning 2 syringes, one for contrast, one for saline. If you see a single head, that's going to be attached to a really, really old CT system, or it's going to be in like a vet clinic or something like that. They really kind of need the saline to maximize modern CT systems' abilities to produce high quality images. Because what they'll do is they'll do like it's called a digital subtraction shot. They'll do a shot with saline, or they'll shoot a shot with saline of the patient, and then so they have that electronic digital image. Then they'll do a shot with a contrast. Now they have 2 images. They have a shot with contrast, they have a shot without contrast. Then what they can do, modern CT systems, they've been doing this a while, so when I say modern, meaning after the 1990s, a computer will take the 2 images, 2 identical images, and pick X-ray or digital images are made up of pixels, all right? So what it does is it takes the 2 images, it compares the 2 images, all the images where the pixels on the 2 images did not change from one shot to the other get deleted. And then they only keep the pixels of the contrast shot where the pixels did change darkness between the two. So if you've ever seen one of those 3D images of a heart, it's just the blood vessels around the heart or something like that, that's how they do that. That's how they do that. Because on the first shot with no saline, or with just saline, all the blood vessels were black. With contrast, they were all light. Whereas all the soft tissue around it stayed the same for both shots. So if you ever see one of those 3D images of just blood vessels and stuff, that's how they do that. That's one of the purposes, one of the uses of the saline. There's a few others, but yep. Now, so that's true for both CT and MRI injectors. Angio injectors don't use saline. Angio injectors, they're all just single head injectors, just one syringe, and it's just the contrast syringe. And I talked about the heaters and the purpose of the heaters. I already dealt with this, all right. For every shot, you have to have a flow rate, you have to select a flow rate, a volume, and a pressure limit. And then this is what we're going to talk about here in a second. There's other parameters that can be selected, but these have to have some value to them. The other ones that I'm going to talk about can be left blank, and they are, not yet, a multi-phase or multi-level injection. So what I was talking about, what that is talking about, so this right here, this shot right here. So I have this protocol set up right here. It's green, so that means we're shooting contrast. It's a flow rate of 5, a volume of 20, pressure number 300 psi. If I select this one, for instance, all right, you see there's a whole bunch more numbers on here, all right? So you see a green line, then a blue line, a green line, blue line, green line. All right, this is a 1, 2, 3, 4, 5, 6. There's six rows here, all right? This is a multi-phase injection. This is a 6-phase injection. What that means is the very first line here, 10 and 200. Who the heck did this one? This is not realistic. Students must have done that one. All right, flow rate of 10, a volume of 50, and it's green, so that would be contrast. Then second phase down here, it's blue, so that means we're going to move to the saline solution, and that is a flow rate of 5, a volume of 5. Then we go back to a third phase, back to green, back to contrast. Fourth phase is back to saline. Fifth phase, more contrast. Sixth phase, saline. This is a 6-phase injection, and now it's a 5-phase injection. So back in the day, they used to be called levels, but in the 80s, around there, they got rid of the word levels and they just started calling them phases, right? So a multi-phase injection, and let me get rid of these. So a multi-phase injection, what will happen is on this particular shot, we're going to shoot contrast and we're going to follow that up with saline. Now, to the injector, that's one injection, right? There's not a pause between the two. So what will happen is, again, I'm going to jump ahead here. I'm going to arm my injector and I'm going to perform my injection. So right here, you see the lights flashing. That's the visual indicator of the operator that we are going to shoot a shot here. And so right now I'm going to shoot contrast, flow rate of 10, a volume of 50. Then we're going to move to the saline, flow rate of 5, a volume of 10. So I'm going to hit flashing light, means when I hit the start button, we're going to start. So first, we're going to shoot contrast. As soon as that injection's over, immediately goes to saline. Should have done more saline. That was anticlimactic. But that is one injection. So that's a 2-phase injection. All right. Any questions? Different injector models. Some will do 4 phases, some will do 6 phases, some will do 8 phases. It's kind of depending on the machine and the model. But pretty much every injector is capable of a single or a multi-phase injection. Any questions on any of that so far? Yeah. I'm sorry, say that again? Yes. Yeah. While they're doing it, because a lot of teams, and I haven't gotten to it yet, but there is something called ISI, Imaging System Interface. So the actual injector will electronically interface with the imaging system so that it can be set up either way, where the X-ray exposure switch starts and stops the injector, or they can set up that the injector start switch starts and stops the X-rays. Okay, that's not always the case. They don't always use the imaging or the interface capabilities, but they often do. Right? It's not uncommon at all. Sometimes yep. All right, holding a pause. Now what this is, all right, now hold and a pause seem like they're the same thing, but there is a difference between a hold and a pause. All right, now if I do a hold, all right, so right here, so now we have a two-phase injection, but there's a hold between the two phases. All right, so I'm going to shoot contrast, then there's going to be a hold, then it's going to shoot the saline. Now a hold is a permanent stoppage of the injection until the operator hits the go button and it continues on. So for a hold, arm it, I'm going to shoot my shot, I'm going to do the contrast. Contrast is done. Now it's on a hold, and it will hold for I think 20 minutes before it just says you guys must have left, and then it just resets itself. So it's still armed. See the flashing lights, so it's still good. It's just waiting for the operator to hit the start button again, and it will continue on to the next phase and complete the injection. That's a hold, right? Now a pause is the exact same thing, but a pause is for a specific length of time. That is literally the only difference between the two. So if I change this to a pause, it's going to ask for how long? We'll say 5 seconds. So now when I do this shot again, contrast, 5-second pause, and then without the operator interfacing with it again, when the 5 seconds is up, it just automatically goes to the next phase. All right, that's the subtle difference between a hold and a pause. I don't think, it's rare that they use a pause. Pretty much anytime you see a protocol like this, it's a hold. I've never, because when we get these, we buy these injectors used, obviously, so we'll get them, and there's always the protocols that are stored in memory when we get it to, for training. We'll go through the protocols. I've never ever seen a pause in it's stored in memory. It's always holds, always holds. Delays. There's two kind of delays, but they go by 3 different names. So we have an imaging system and we have the injector system, right? And they work together, right? They have to be used in tandem with each other. So there are inject pause, there's inject pauses, and there's CT. Oh man, what am I? What are we talking? Delays. Yeah, sorry about that. Scan. Man, I told you it's been a year. So there's inject delays and there's scan delays. Can't believe I forgot that. An inject delay is just that. All right, the injector. We're gonna shoot both of the systems, the imaging system and the injector system, and they're gonna typically shoot at the same time. But sometimes we want the X-ray system to start doing its thing before we actually start injecting fluid into the patient. That is when we would install an inject delay. Now, an inject delay is one of the buttons on the protocol. You'll say, yeah, Paul, inject delay 2 seconds. So what will happen now is when I hit the start switch on the injector, it doesn't immediately start injecting. I hit that start switch, it counts down 2 seconds, then it starts injecting because it wants to get the CT system rolling and start the scanning before we get to the fluid. So an inject delay, that's the same for all 3 types. CT, MR, angio injectors, they're all called inject delays. Now, the other half of that is where we're gonna do the injection, but we're going to pause the imaging system. That goes by 2 different names. It's called scan delay and X-ray delay. They're the same exact thing. It's just for CT and MR injectors. It's called scan delay because it's a CT scanner or an MR scanner. Whereas for your angio injectors, which is more of a traditional X-ray system, that's called X-ray delay. Same exact thing. We'll hit the start switch, the injector will start injecting, and then so many seconds later, the imaging system will automatically start doing its imaging systems, or it's producing its images. All right, so small difference, but or 2 different types of delays, but they go by three different names. KVO, if you guys are infusion pump folk, you know what KVO is, stands for keep vein open, because for CT and MRI injectors, they actually use an IV needle for the injection. If there is a long pause between fluid getting injected into the IV needle. The end of the tip of the IV needle can actually form a blood clot at the end of it. So what they do to prevent that from happening is they can turn on a KVO function. Not every injector system has KVO, but a lot of them do. KVO, what that does is, and it gets set up in the setup menus, and this can be set up a whole different bunch of ways, but anywhere from every 10 to 60 seconds, we're just gonna inject 1 milliliter of fluid, just enough to keep the tip of that IV needle from clotting. All right. Test injection. This is for CT and MR injectors. Angio injectors don't do this because an angiographic procedure is almost like a surgical procedure. There's a doctor, there's a cardiologist in the room, there's X-ray techs, and there's like 3 or 4 people in the room while we're doing this, and everybody's in the room during the entire procedure. CT and MRI procedures, that's not the case. Patients on the table, they are in the room all by themselves, and everybody's the CT techs and MR techs, they're behind the glass in the control room doing it from there. Now, CT and MR injections are done through, like I said, an IV needle. A lot of times the patient will show up from ER or ED already with the IV needle in them, okay? Or when they get there, if they don't, they need to put the IV needle in themselves. To make sure that we actually got the needle in the vein and we didn't just plunge it into soft tissue, before I go shooting this first phase here of 50 milliliters of fluid, let's make sure we actually got in the vein. So what they'll do is, for phase 1, this is only phase 1, you select phase 1, and one of my selections here says contrast, flush, or cancel, but one of the options is test. So I've hit test inject. That shows phase 1 now is going to be a test injection, and the operators can set this up, but it's typically going to be saline, and it's typically going to be obviously a very low flow rate and a very relatively low volume, like 2 or 3 milliliters of fluid, not a whole lot. So what they're going to do is before we go on to firing 150 milliliters of fluid in the patient, we're going to test and make sure we actually got the IV needle in the vein. So the very first shot is going to be a test injection, and so my first inject here, I'm going to set the system up. All right, so now when I hit the start switch, we're just going to do a test injection. It's going to be very, very low, very, very quick. So if you watch, just watch. So it's going to be the saline side. So just watch this syringe here, because you won't be able to see this syringe move because it's going to be very, very little. So just watch this button or this knob here turn, and that's it. That's the test injection. But you'll notice that it didn't just automatically go on to the next phase. It was a test injection. It's built into the system. After a test injection, the system goes into a hold. Now the operators can come in, check the area, make sure that the arm didn't swell up or whatever. Yep, we're good. We hit the vein, then we'll move back into the room, and they will carry on with the rest of the injection. Okay, so that's the test injection. Any questions? All right. How am I doing on time? All right, just some components on here. All right. So right here we have, all right, so right here we have, you notice we have my forward and reverse buttons. All right, these are obviously there to move the plungers up and down. But you'll notice if I hit the forward reverse button, nothing happens. All right, now the reason for that is it's a safety feature. We don't want the operator to grab the head and move it and accidentally move the piston forward or reverse while we're hooked up to a patient. So the forward and reverse buttons don't work until we hit the enable button right here. Now it used to be called enable, and this is on the Stellan. It used to be called the enable button. And I did notice about 10 years ago, they changed the name to move piston button. I guess people were getting confused. So the enable button or the move piston button, you press it when it lights up. Now the forward and reverse buttons actually work. For filling and priming. Yep. The other way to move the pistons up and down is they can do it manually, and then you're not going to use a manual knob. I just want to move it forward a few milliliters or whatever. You're going to move it significantly, you use the forward reverse button. If I just want to get a little air bubble out, that's what you typically use the manual knobs for. Any questions on that so far? Was that the end? No, I didn't think so. You guys saw that earlier whenever we arm the injection. So you see, I've done this without explaining it, but I'm not going to explain this one because this is a stone only thing. But right here, it says a little button right here. So now when I hit, like we're filled up here, if I hit the inject switch, nothing happens. Again, it's a safety feature. The injector won't shoot the injection until we arm the injector. All right. There's a little button right here. Every injector module has it. Arm. Question pops up. It says, have you checked for air? Now here's the thing. Contrast injectors, and they all do this. Contrast injectors, obviously we're firing fluid into a patient. We don't want to fire air into a patient. So every single injector, you have to arm the injector before it'll actually shoot. And so whenever you hit the arm button, a question will pop in one form or another, say, have you checked for air? The system, and the reason I'm bringing this up, the system does not check for air, all right? It does not. You'll notice I have nothing but air in my syringes. I've been shooting this thing all for the last hour, all right? It says, have you checked for air? And the operator has to hit yes. That is the manufacturer's get out of jail free card. Because now if that kills a patient because we fired air bubble into them, they can prove, well, it wouldn't have done that if you didn't say you hadn't checked for air. So, and this comes up, I get this call, I was gonna say like once a year, it's been a while, but twice in the last year, I'll get a call from a lawyer's office wanting a independent third-party subject matter expert opinion on why this injector killed a patient. Twice in the last year I've gotten that call. As a matter of fact, one time the patient didn't die. They fired like an empty syringe into it, and I guess they noticed before it was lethal, but apparently the patient's, this is according to the lawyers, he's never been the same again, but they wanted my opinion on what happened. And I had to tell him the bad news. Like, no, the hospital's responsible for that. The x-ray tech screwed up because he was giving me details, and it wasn't this model, it was a different model. I said, yeah, there's no way that the machine did that without the operators telling it to do that. So I didn't hear back from those lawyers. It's weird. All right, so yeah, so that's the arm light. So once I've armed it, now the arm light is flashing, and that's the visual indication to the operator. All right, when you hit the start switch, we're going. All right.